Okay, so good morning everyone. I am Lotta Jokiniemi. I am a postdoctoral fellow in the nuclear theory group at the ICCUB. And I'm going to talk about searching for new physics with the help of neutrinoless double beta decay today. So first, some motivation for my research. This is actually related to Antoni's talk yesterday. So he talked about the neutrino physics, and I'm going to cover that from the nuclear physics side. So as we all know, the current knowledge of particles and the interactions between them is based on the standard model of on particle physics. And according to the standard model, neutrinos are extremely weakly interacting and massless particles. But as Antoni told us yesterday, we know from solar neutrino experiments that neutrinos have to have a non-zero mass in order to be able to oscillate into different flavors. So we yet don't know what is the absolute mass scale of the neutrinos. So from the solar neutrino experiments, we only know the differences of the squares of the masses, but we don't know what is the absolute mass scale of the neutrinos. Also, we don't know what else might there be beyond the standard model. And maybe the most important questions for me is what could we learn from double beta decay of nuclei, which I'm going to talk today. Okay, so this is not certainly a new idea, but actually it was first proposed by Maria Goeppert-Mayer in 1935. I think my grandma was about 13 years old that year. And a couple of years later, Ettore Majorana in here proposed the idea of Majorana particles, meaning that particles can be their own antiparticles. And again, a couple of years later, Wendell Furry came up with the idea of neutrinoless double beta decay. And that is where this story began. Okay, so what is a double beta decay? The double beta decay may happen when the single beta decay is not energetically allowed. So for example, if you look at this nucleus in here, you can see that the single beta decay is not allowed because the final state would be higher in energy than the initial state. But on the other hand, this nucleus in here may double beta decay straight to the nucleus with 2 more protons, which is lower at energy. And as I maybe already told, there are 2 modes of this decay. First one, which was introduced by Maria Goeppert-Mayer, is the standard 2-neutrino double beta decay. And the second one is the yet hypothetical neutrinoless double beta decay, which was introduced by Wendell Furry 4 years later. Okay, so what is a 2-neutrino double beta decay? There are 2 neutrons inside the nucleus decay into protons. I'm sorry, this figure might be too small for those in the last rows. And 2 electrons together with 2 antineutrinos are emitted. And this is a second-order weak process which is allowed by the standard model of of particle physics. And actually it has been observed in 11 nuclei already. But just to give you some perspective, there are about 5,000 known nuclei. So it's not really it doesn't really happen often. And furthermore, the half-lives of this decay are of the order of 10 to 20 years or longer. So it's comparable to the square of the age of the universe. So you may get some idea that this is actually a rarest measured nuclear process. Okay, so what is neutrinoless double beta decay then? It looks like 2-neutrino double beta decay, but as the name suggests, there are no neutrinos emitted. But actually the neutrino, which is emitted in one nucleon, is absorbed by the other one. And this process in here requires that neutrino is its own antiparticle, or Majorana particle, if you wish. And this would be the first Majorana particle that we know. It also violates the lepton number conservation law of the standard model by 2 units, since there are two leptons created in the process, but no anti-leptons. And sorry, I will go back. And furthermore, the half-life of the process is inversely proportional to the square of the so-called effective mass, m beta beta here, which consists of the neutrino mixing matrix and the neutrino mass states. So this means that if this process was measured, we could get a hint of the neutrino masses, not only the squares of them, or the square differences of them. But it has not been measured, at least yet. Okay, so the half-life of neutrinoless double beta decay looks like this. And here is what would be measured, so the half-life of the process. And on the other side is the new physics, meaning the effective mass containing the neutrino masses that we would like to extract from the half-lives. But as you can see, there are a few things in the middle. First, there is a fourth power of the axial vector coupling constant, Ga, which for a free nucleon it's approximately 1.27, but in a nuclear medium it may be quenched, meaning smaller than 1.27 or not. This is under debate at the moment. And next there is a phase space factor which contains the physics of the 2 electrons that are emitted in the process. And this factor can be solved from a Dirac equation, and this can be done pretty accurately, so I'm not going to discuss this more. And then there is a square of the nuclear matrix element, and this has to be provided from nuclear theory, such as quasi-particle random phase approximation or nuclear cell model. And why I'm mentioning these 2 models in here is because we are using these models at the nuclear theory group at ICCUB. But there is a but. Namely, the matrix elements coming from different nuclear theories, which are shown different markers, disagree by a factor of 3 or more. So they are all over the place. And remember, we need the square of the matrix elements in here. On the other hand, the experimental side is not easier at all. So this is what they want to measure. This large bump in here is, I'm showing the energy spectrum of the emitted electrons. And the large bump in here is the 2 neutrino double beta decay. And it's a wide bump since the emitted neutrinos carry away some of the energy which is released in the process. But for neutrinoless double beta decay, since there are no neutrinos emitted, the electrons carry away all the energy, and it makes this a sharp peak at the Q value of the process. And by the way, this is exaggerated in order to you to see this peak, so this would in fact be smaller. And what we know from the current experiments is that the half-life of this process would be of the order of 10 to 25 years or longer. And remember, for 2 neutrino double beta decay, which was the rarest process at the moment, it was of the order of 10 to 20 years. So this would be even more rare. Okay, a few words of the current status of the double beta decay experiments. So there are many experiments worldwide, a few in Italy, a few in the US and in Japan. And there is also one in Spain called NEXT, which is situated at Canfranc, deep underground. And yeah, this experiment should start data taking soon. Okay, and from the current experiments, the most stringent half-life limit is for 76 germanium, which is one of the candidates. And for that, the half-life limit is of the order of 10 to 26 years already. Okay, and here I'm showing the effective neutrino mass as a function of the lightest neutrino. And in the normal hierarchy picture, the neutrino masses would be ordered like this. So the M1 would be the lightest, and then M2, and then M3. But there is also another possibility, namely the inverted hierarchy, where the M3 would be the lightest particle. Remember, we only know the differences of the squares of the masses, but we do not know the order of the masses, for example. And in here, the red band is the so-called normal hierarchy region, and the green band is the inverted hierarchy region. And combining the current half-life limits and the matrix elements and the other ingredients, we are approximately in here. So we are not yet reaching the inverted hierarchy region completely. But the goal of the next generation experiments is to cover this region and thoroughly study it. Because, yeah, as I may not mention, these two regions are those possibilities where we could find the double beta decay. But in order to plan these next generation experiments, we really need to get the nuclear matrix elements under control. So this is what I'm going to talk about today. How could we do that? So first, you might think that we could improve the double beta decay calculations. And this is what we have done. So, okay, let me say a few words what these matrix elements contain. So as I said, the half-life of the double beta decay, neutrinoless double beta decay, assuming the so-called standard mechanism, looks like this. And here the matrix element, which I denote by ML, can be written like this. So it contains the Gamow-Teller, Fermi, and tensor parts. But there seems to be something missing. Namely, in 2018, Vincenzo Sirigliano and others published this paper where they introduced a new leading order contribution to the neutrinoless double beta decay. And this contribution was missing in all the calculations. And what they say in here, the abstract, this contribution might be relevant for the experiments. So we need to add this additional term in here in the half-life equation. And by S, I mean the short range or contact term. Okay, and this was already studied in ab initio framework for the lightest nuclei, since they cannot reach the heavier ones. And they saw that for helium, adding this new term increases the matrix element by 5 to 15%, and for beryllium by 20 to 18%. 80%, sorry. And later on, these studies were extended to the first, or the lightest double beta decay candidate, 48 calcium, and there they saw a 43% increase. And this is, of course, good news for the experiments, since they need the squares of these matrix elements in the half-life. Okay, but how about the heavier candidates? So here at the UB, we calculated these matrix elements for the heavier candidates, and by heavy I mean the candidates from 76 germanium up to 136 xenon. And we did this in two different nuclear models, in QRPA and in nuclear shell model, which I already mentioned earlier. And in QRPA, we saw a 30 to 80% enhancement. And in nuclear shell model, we saw a 15 to 50% enhancement. And I'm showing the results in here. So these curves in here are the integrands. And by integrating over R or Q, which is the momentum, you get the total value of the matrix element. And as you can see in the nuclear shell model, which is shown here at the right side, the matrix elements tend to be smaller than in QRPA. But in any way, it is important that in both of these models, this short-term term was important. So then, in order to study how this affects the interpretation of the experiments, we derived the effective neutrino masses from the current half-life limits and with our matrix element. And we show that by adding this short-range term, which is shown here in the lower bands, we are actually reaching the inverted hierarchy region. So in QRPA especially, we are right at the border of the inverted hierarchy region with the current experimental sensitivities. And to be conservative, we also subtracted this leading order term, since we were not 100% sure of its sign. And if we did that, we of course move further away from the inverted hierarchy region. Okay, so there are also other ways to constrain these matrix elements, and namely using experimental data of some other related processes that can be measured. So one example is the double charge exchange reactions, bit of a mouthful, which are mediated by strong interaction. And they can be related to double beta decay, as shown in here. So this is one of the candidates, 76 germanium, which decays to 76 selenium in the double beta decay process. And this can be related to a strong interaction process like this, where the germanium is bombarded by neon, and then they exchange a charge, and resulting in 76 selenium and oxygen. And this is difficult, yet possible to measure. And actually we have found a linear correlation between these matrix elements of neutrinoless double beta decay and double Gamow-Teller. This is one of the strong interaction processes in all the studied models: nuclear shell model, energy density function as QRPA, and interacting boson model. So this means that if a double Gamow-Teller reaction was to be measured, so we get a Y value in here, we could extract the value of the double beta decay matrix element from it. Okay, and other possibility is to use double electromagnetic decays, namely double magnetic dipole decays, which can also be related to neutrinoless double beta decay. So we can study the decays from the double isobaric analog state, which has the same isospin and spin as the initial state, to the ground state of the final nucleus of double beta decay. And here I'm showing the double beta decay and the double gamma decay that we have been studying. And these double gamma decays are also possible, yet difficult to measure. And we have found a correlation between these two processes too. So here I'm showing the results from the shell model calculations done by Beatriz Romeo and Javier Menendez, actually part of the ICCUB group. And yes, we see correlations, yet different ones in both of these models. And this also means that if double M1 decays would be measured, we could constrain the matrix element by using the experimental data. Okay, so that's it. You can read my summary here. Okay, no, I can also talk about my summary. So, to summarize, observing double beta decay, neutrinos double beta decay would shed light on neutrino properties and physics beyond the standard model. Actually, as controversial as it might sound, neutrinoless double beta decay would be the most robust way to shed light on the properties of neutrinos. And reliable nuclear matrix elements are crucial for the double beta decay studies. And we also saw that adding this new short-range term in the matrix element enhances them notably. And we have also found correlations between measurable processes and double beta decay, meaning that we could constrain the values of the double beta decay matrix element using the data. Okay, thank you.
Thank you, Lotta. There is time for some questions.
This is just a curiosity. What would be like the main consequence of having a Majorana particle in the standard model?
Main consequence? Well, it would allow, for example, neutrinoless double beta decay. That's I guess, the main consequence that I know. Yeah, but also, I guess, other processes that I cannot think of. Also, it has consequences if Majorana particles exist. It would have consequences in like superconductivity, like quantum spin liquids and things like this. I'm not an expert on. Okay, thank you.
Hi, Lotta. Thank you. Thank you very much for your talk. This short-range term that these people, Ciriliano or Van Kolgolf is involved, do they know what is the origin of this short-range term? Is that, I mean, they are fitted to some nuclear observables, or?
No, not really. So it's pure coming from, from theory. So they found that they need this term in both, I don't know if you can read it, in both dimensional regularization and in coordinate space cutoff scheme in order to this matrix element to be renormalizable.
Okay. Okay, and about these correlations, that's very interesting about other, let's say, more nuclear related reactions, or these two gamma decay, or this reaction of double gamma Teller reaction. How experimentally, how are these experiments? Are they feasible? Are they now running, or?
Oh yeah, I should have highlighted that more. But yes, there is a Newman Collaboration in Catania in Italy, and they are actually hunting for the double gamma Teller decays. So their main aim is actually to help constrain the double beta decay matrix element.
So data is expected when, more or less?
They haven't found anything yet, but they are. I think they are upgrading their measurements right at the moment. But as I can explain, as I am showing this figure in here, this is really difficult to extract from the measurements since there are many competing processes. As you can see, like germanium can decay to here and then to here, or there are many paths that they have to be aware of in order to extract this. Okay, thank you.
Okay, we should move on. Let's thank Lotta again. Thank you.